All right, this is continuation of the first section of this training material here. Now we have our battery bank size. Total battery, we need 3 battery. The DC system voltage is 48 volt. 48 volt divided by 48 volt, we have 1 battery bank in series times number of battery string, 3 string. So we need 3 battery. That is how you know how many battery you need. We need 3 battery. So now it's very important here to understand the DC system voltage and the battery voltage. If we're using 12-volt battery and our DC system voltage is 48 volt, we're going to be able to divide the 48 volt by 12 volt to give us here. Let's go right here. Let's move on here to see. So in this example, this is for a lead acid battery. You have the DC system voltage of 24 volt and your battery voltage is 6 volt. So 24 volt divided by 6 will give you battery in series 4 multiplied by a number of battery in parallel, you have 12 battery. So this is the system voltage, which means the solar panel voltage is 24 volt. So solar panel comes in, the system volt could be 12 volt, 24, or 48. So you have to fall on one of those. You divide by the battery volt, which is 6 volt. The total number of battery you need is 12 battery. So it's the same old thing here with the lithium ion battery. Same old, same old. Let me go back. If you look right here, total battery is 3. So our battery is size. So that's how you size the system battery. Now, DC coupled standalone residential system design peak sun hour. You can use the PV wax to find these. Now, over the next couple slides, we will identify a number of different variables that will be used in PV array size. In order to calculate the necessary array size, we must first identify the solar resource available at the site. For this design, we use a PV wax at the location close to the installation site to get the average peak sun hour per hour. When importing information into PV wax, we use a system size of 1 kilowatts, which basically gives us a peak sun hour per day for each month. System size does not matter in this case because this is an off-grid system. We use a site prefer array type, prefer a tail angle of 40 degrees and an azimuth of 180. We can see the peak sun hour vary from a low of 4.51 in December to a high of 7.1 in June. So very important. Temperature losses are calculated separately from the rest of the array power losses because like peak sun hour, temperature in most locations, though not all, varies throughout the year and are calculated on a monthly basis. The required data are the temperature coefficients of maximum power for model TKPM in decimal, not percentage form. If not available, use an estimate of negative 0.5% or 0 degrees Celsius or negative 0.005. The average high temperature for each month for the particular location, which are available from variety of sources online. You can know that. Varieties of sources online. When sizing a PV array, we also must first consider all of the losses that will reduce the array output. Some losses vary by month and may be site-specific, such as the sorting, the shading, the snow. Other losses are typically statistics and are the same or very similar for most installations. These include the model mismatch, the wiring losses, the connections losses, and the model power tolerance. You read these yourself in there. the array sizing factor. You want to take into consideration the load, the peak sun hour, the monthly weather variables, the battery efficiency, the convection losses, the temperature losses, the charge controller type and adjuster, the array power. Divided by the battery efficiency of 0.95, divided by the conversion loss of 0.98. Now, if you look down here, there is the information you need. The temperature coefficients is there. The temperature coefficient ISP is here. Even the open cell temperature is here. It's right on the model. The PV model have all of these information here. All of those informations are right there. The PV array wax is 3,573. The model wax rating is 2,265. The PV array divided by the model ratings, 265, we give you number of model needed, 13.5. The basic calculation is from left to right. Average daily energy watts hour divided by peak sun hour divided by Monday weather data, variability, Monday weather data variable, divided by battery efficiency, divided by convection losses, divided by temperature losses and charge controller type adjuster, divided by array power losses, divided by required PV array watts. Understand each time we divide by a loss factor is in decimal from the required size of the PV array is increased. Four of the factors vary by month. The load in this case is 6,021 watts hour daily from March through September and 7,459 watts hour daily from October through February. Remember, the efficiency of the inverter has already been accounted for in the average daily energy value. Peak sun hour, which can be obtained from the PV wax or another source. Temperature losses, as calculated a few slides back. The array power losses include statistics and variable factors. Monthly and account for higher snow and shading losses typically occur in winter. Battery efficiency depends on the chemistry. Always consult the manufacturer in this example. The lithium is 95%. When running the formula by month, it is easy to identify the seasonal variable like loads and peak hours. If there were high load in a specific month, the required PV array size will be larger for that particular month. In performing the calculation result in minimum required PV array size to power the load for each month. The load in January is 7,459. The peaks on hour then is 5.05. You divide that by the Monday weather data variable, 0.70. Divide by the battery efficiency. Divide by the convection losses. Divide by the temperature loss. Divide by the charge controller type adjuster 1. Divide by the power loss, 0.81. Require PV array watts. So we have 3,575. The minimum array size. You run it up to 14. Okay. So if you look here, I'm going to explain this whole graph, whole actual area here. Very nice. I'm going to go back. I'll go back up a little bit. If you look at the system information now we have is the discover 42 minus 48 minus 668, 48 volt, 6,650 watts hour. Parallel equal 19,950 watts hour. The day of autonomy is 42, is 2 days. The maximum discharge limit is 95%, is 90%. $42, 48. Sorry. Okay. So if we look here, it's beautiful. 7,459 watts hour dated times day of autonomy divided by the voltage. We got 16,000 watts hour here. That is how much watts hour we're gonna need. That watts hour 16,576 divided by the battery capacity of 6,650. We got 3 battery. We talk about that. The volt of the system is 48 volt, and the battery volt is 48 volt because it's lithium ion battery. The battery volt and the system will have to match. If you're using a lead acid battery, you can pair the battery in series to increase the voltage to get the required voltage for your system. But for lithium ion, you cannot do that. You cannot pair them in series. Now the peak sun hour. I'm gonna do something right here. I'm gonna go to the PV watts calculator. I'm gonna show you the PV watts calculator. pvwattscalculator.org, pvwatts.nrel.gov. This is where we have our information from. That's the use over there. So somebody will say, oh, this is just American system. How can this work for Liberia or Africa? So I'm gonna come here. I'm gonna say LWA LIB. Let me see how to find that. Yes, the international, we have it here. No, let me go back. Now, Liberia, the weather data they use for West Africa, the closest country to Liberia is Senegal. Similarly, we have similar weather, similar kind of climate. So if you notice that they're using Dakar, Senegal, which is about 735 miles. So they're trying to say is that in that region, about same region. So if I pull Ghana here, it would give me the Ghana location. Because there are a lot of things we are missing on. Accra, Ghana, we have right here. Accra, Ghana is closer to Liberia than Senegal. I'm gonna go change the location to Sierra Leone. Dakar, Senegal. So there we have comparison. So Sierra Leone, Liberia being close, have similar weather. So here we see our DC system. We take this to 1. We will change our tail angle. Azima is 180. Tail angle, what was the tail angle? Fixed roof mount, yeah. The lost, system losses. Conversion loss, 0.98. You should just leave it there. If I change it, doesn't make any big difference. Oh, losses, we have the sorting. That's if they have sorting in the area. We may not have sorting, we have no snow. Change that to 10% losses. Save it here. Residential. Here you go. This is the data you have. AC energy kilowatts hour. This is the peak sun hour. So that's how much of a sun we have in that area. The peak sun hour right here. I'm gonna print this. How much of a peak sun hour? So they're saying here, we have sun, good sun. Sun is always high. Your annual 5.74 annually, and your AC average will be 505,750. If you look at this example here, the peak sun here, this is the average daily energy based on their calculation. The peak sun hour here is 5, 7. This is the average. This is the average 4.51. Our solar energy, the annual is 5.71. So you see that's where they got that information from. Very important information. This information, the Monday weather data variables, you're going to add that in the chat. The battery efficiency, you're going to get that information. The conversion losses, you're going to get that with you're going to get that. Is the information you get. But they're showing you the required PV array watts for your system here per month. That's where they're showing. So I want you to just refer to the average daily energy used in wax hour per day comes from a load analysis which vary by winter and summer season. The peak sun hour for geographic location from the system in the tilt angles and orientation of the PV array were obtained from the PV wax. Peak sun hours data is an average over a long period of time. Since it is an average, the actual monthly PSH can be varies on about 30% different, about 30%. To account for this, we use a monthly weather variable factor of 30%, which is 0.7. Battery efficiency for the chosen battery model is 95, which is 0.95. Since we are using an MPPT charge controller in this DC coupled system, we must debrate the array output for a conversion loss through the charge controller. This manufacturer rates the charge controller efficiency at 98%, so we have 0.98. Since we are using MPPT charge controller, we don't need to debrate for charge control type. Array power losses vary according to system locations in particular of the installation. We use the monthly array power loss factor from the chart provided. Yep, DC to AC size ratio 1.2%, the inverter efficiency 98%, the system losses 21 array. So I just did this using the PV wax. So you can use your PV wax to get the these information when you are sizing your PV array. So they are saying here on the array over here, the required PV wax 3,575. That is the minimum array they're going to use. For this system, the smallest array you can use would be 3,575 to charge that battery. That's the smallest you can use, 3,572. It can be lower than that. Can be. Using all of the factors from the previous slide, the minimum PV array size based on the required energy can be calculated. This will be done on monthly basis. So the different seasonal load require verifying effective of temperature, verifying array power losses, and the amount of peak sun hour can be accounted for. The basis calculation is from left to right. Average daily energy wax hour daily divided by peak sun hour divided by monthly weather data variability divided by battery efficiency, conversion losses, temperature losses. Understand each time we divide by loss factor in decimal from the required size of PV array is increased. 4 of the factor vary by month. The load in case 6,021 wax hour monthly from March through September, and 7,490 from October. The battery efficiency depends on the chemistry. Okay, so this is a PV model we're using. The Eagle 660P, 265 to 285 watts. This is the model information. This is the model from the PV watts we have here. The maximum power is 265 watts. The maximum power voltage, 31.48. The maximum power current, this is in amps. The open circuit voltage, 38.64. Now, somebody will be confused. They say the open circuit voltage here is 38.64. Why is our nominal voltage 48? Once your system voltage passed 36 on the PV model, you fall in the range of 48 volt. So always know that you're in the range of 48 volt. So when you're sizing your system, you should know that you are in the range of 48. So that's just a simple refreshment. It is common practice when designing a system to size the array and then go to your distributor and decide which model will best fit the design. Of course, model availability, affordability, and customer or installer preferences also must be taken into account consideration. In this case, we are going to use a Jinko Eagle 60p model. There is a 60 cells PV photocrystalline model which comes in power range from 265 watts to 285 watts. We have decided to use the lowest power 265 watts. To determine the number of models needed to divide the required PV array watts from the selected month. In this case, from the selected month. So we selected December. In this case, we use 3,572 watts from December by the model power rating of 265 watts. This gave a total of 13.5 needed to meet the array power, the average to meet the array power requirement. So 3,575 watts divided by 265 watts equals 13.5. We're running out to 4 to 14. Charge controller specification. This is a charge controller. We have this charge controller here that can handle 24, 20, up to 60 volt. That's a good charge controller. It is good to design practice, although not required to use the same brand. Sometimes good is required. Not you may not even have the budget to buy the same brand, but it's good practice. This is very important. Notice that the maximum PV open circuit voltage is limited by the Connex MPPT controller to 150 volt. This value will be used in the next calculation to determine the maximum number of modules that can be wired in series according to the data sheet. The Connex MPPT charge controller has a maximum output current rating of 60 amps and can be used with a 48 volt system. Although note is that the maximum open circuit voltage from the array of 150 volt must include a temperature correction factor. We cannot simply use the model VOC when choosing how many modules are wired. The following slide will show the process. Here we are. Maximum module in series. The minimum temperature is -21. Where did we get that data from? Minimum temperature. I want to make sure we get a -21 minimum temperature, -21, minus the STC cells temperature of 25. STC cell temperature of 25. So we had a degree, which is -46. We take the -46 multiplied by the TK volt, -0.31. This is right here under the PV model. -0.31. Temperature coefficients volt. That's what they're asking for there. So we have a -0.31% equals 14.26% difference. Now we have the maximum system volt input is 150 volt divided by the model volt of 38.6 times 1. Now you're going to know what the 1 is. Look on down here. According to the model data sheet, the model volt is 38.6 volt, and the temperature coefficient of of negative 0.31 divided by essential shade extreme annual minimum design drop bulk temperature at location of this PV system is negative 21 degree. We need to determine the correct module volt at this load. The first step is negative 21 Celsius minus 25 equals 46, okay? Negative 46 Celsius times this equals 14.26. Now, the maximum module in series, 150 volt, divided by the volt of the module times 100%. So that one is 100%, equal plus 14.26%. The maximum module in series, 150 volt divided by 38.6 times 1,100, 1,426, 150 divided by 44.1 volt, we got 3.4 maximum module in series. 3.4 maximum, so 3.4. So we're going to run it up to either 4 or we run it down to 3. So it's the same thing here, same calculation. To know your model in series and parallel, maximum source socket in parallel. These are all the calculation, PV source socket. The maximum PV array ISP controller, 48. The PV source socket, 90.038 ISC. The maximum socket in parallel is 5.3. We're going to round that out to become 6. Yeah, I'm trying to close it. I've been doing it. I got some things to do today. Yeah. I cannot end this whole thing because you have to run through it. I don't want to run through it. So I will have a next class. All right, guys. At this junction, I'm going to stop to page number 21. Page number 21. I don't want to run through it. I want to present the material right. I don't want to run through the material. Yeah. I want to present the material right. Yeah. Okay.